All right, good afternoon. This is our screencast for Project 2. In Project 2, our goals are going to be to extend our cubic equations of state, namely SRK and Peng-Robinson, to model binary mixtures. And in particular, for this project, we will look at modeling excess enthalpy. Okay? Excess enthalpy of a condensed phase at 1 bar. And while we're at it, since we're working with cubic equations of state allow us to model pressure dependencies of properties. So while we're at it, we'll calculate the pressure dependence of delta H of mixing. Okay, and where this will be useful is when we're modeling condensed phases. Typically, we'll assume enthalpy and Gibbs free energy. Our excess properties are all pressure independent, and so we'll see where that arises, or why that arises, and over what ranges that approximation is reasonable. Okay, and so before we jump in and I demonstrate how to use the MATLAB code and to make some predictions, I just wanted to touch base again on cubic equations of state and extending them to mixtures to put things into perspective. Okay, and so this slide just contains our SRK equation of state as we first saw it back in chapter 2. Okay, and the key things I want to point out is, remember this first term, okay, with my B's meant to account for the size of my molecule, my molecular size term, whereas A accounts for intermolecular interactions, right? A's, corresponds to the strength of interaction between two of those molecules in solution. Okay, A and B we can relate to their critical properties and eccentric factor for the case of SRK via these equations. So while this works really well for pure components, and we can use it to predict pure component properties or phase behavior of a pure component system, extending it to mixtures becomes complicated. Okay, so here for this pure component system, I'm able to relate A and B to pure component properties. The challenge we have is when we try and use cubic equations of state to model mixtures, is in a mixture we have both interactions between, say, component 1 and component 1 and component 2 and component 2, but now we have cross interactions, right? Interactions for a binary system would be, or cross interactions would be interactions between component 1 and 2. Okay? And so it's challenging in terms of how can you predict how these two different molecules are going to interact just based on pure component descriptors. Okay? And so we have to introduce mixing rules. And the challenge of mixing rules is always still, okay, I can have some of sort of mathematical relationship to take my two pure component descriptors and predict what that might mean in terms of cross interactions. But at the end of the day, we need to fit our mixing rules to available binary data. Okay, and so what's listed here is just a modified van der Waals mixing rule, where the B of my mixture is just arithmetic average of the B's of my two pure components, right? Or here it's written as a molar average. Okay, and then in my expansion here for A, okay, the idea is we're going to take our cross interaction, right, A for a 1-2 interaction, and we're going to take that as a geometric average, and then we're going to multiply it by this correction term 1 minus Kij. Okay, so when Kij is 0, then my cross interaction is just the geometric average of a 1-1 and 2-2 interaction. Okay, when Kij is let's see, so 0 is, it's geometric average. When Kij is greater than 0, then this term 1 minus that term is going to be less than 1. So we're scaling down the cross interactions relative to what we would predict via that geometric average. And when Kij is less than 0, we would strengthen our cross interactions relative to that geometric average. Okay, and so we'll look at a couple of examples and see what this means in practice. Okay, and so the challenge with cubic equations of state is if I want to use them to model a binary mixture, I need some binary data available so that I could fit Kij. Right? So good binary data would be something like a virial coefficient, so something directly related to two-body interactions. But in theory, you could fit it to anything. Right? If I had a available experimental VLE for that binary system, I could adjust Kij to minimize deviations between my reference data and what I would predict, or I could do a similar fit to any other binary data. So in this project, we'll use delta H of mixing, or excess enthalpy 1, because as we've already discussed, excess enthalpy is related to intermolecular interactions. Okay, and then 2, there's a database readily available of properties that we can work with. Okay. All right, so I'm going to close this up. And much like the last project, okay, so in our team drive, we had a project 1 folder. Now I have a project 2 folder. Okay, and so within it, I have a system assignments file. Okay, it's the same as this one. I've just opened it up twice. Okay, so what you'll find is the link at the very top. Okay, this is going to be a link to database. Let me close it so I can reopen it. A database of free data available from DDBST. Okay, so when I type that link in, it brings me to this database from DDBST of excess enthalpies. So we haven't talked about excess properties yet, but in the case of enthalpy, the excess enthalpy is the same as the enthalpy of mixing. Okay, so you can interpret this as enthalpy of mixing. Okay, so they have a database of enthalpy of mixing data, which we can use to fit Kij, right? And what I want to look at is how sensitive those predictions are to Kij, and then also for very non-ideal systems. So we'll look at some associating systems to kind of get an idea of what the limitations of these equations of state are for modeling delta H of mixing in binary systems, or just modeling binary systems altogether. Okay, so when I go to that link, okay, actually I'm going to go back to systems assignments. Okay, so I have everybody from the class. Okay, so I have your name, and then I have listed a system. Okay, and what I mean by system here is when I go back to the database, okay, you'll notice they have things broken up as a list of components. Okay, and so if I were to click on acetonitrile, which is just the first one, it brings me to the first one. Okay, when I say systems, all I've done is I've listed all of these components. So the components that are condensed phases. Okay, so liquids at ambient conditions. So I didn't do naphthalene. I also skipped over. Here I have methane, nitrogen, potassium chloride, and sodium. So I skipped over those as well. Right, but if I look at acetonitrile, right, so if you're assigned acetonitrile, what I'm referring to is this group of data. Okay, so if you have acetonitrile, for example, you should be looking here. Okay, if you have ethanol, right, here's your list of all the systems available, or data available for ethanol. Okay, so what I would like you to do is for your system, all right, so again, by system, you just, I should have, let me scroll up to the top. All right, for your system, all right, so say I have water, all right, I click on it. Here's a list of all of the binary systems for which data is provided. I would like you to choose at least 10 of them. Okay, so choose at least 10 of these binary mixtures and try and come up with a good variety. So if I'm looking at water, yeah, water butanol is good, but it would also be good to look at water cyclohexane, right? Not just water with an alcohol, but water with an alkane. So regardless of the binary system you're looking at, the calculations will be just as hard, the analysis will be just as hard, right? Or just as hard or just as easy. But we want to look at different systems so that we can get some different results to kind of get a feel for how these things perform. Okay, my one note is I mentioned that in the component list I excluded non-condensable systems, so things like nitrogen and methane, things that are gases at room temperature. I also did include salts, or sodium and potassium chloride, and I'd include naphthalene, something that should be solid at room temperature. So I should add, because as I look at this, right, I wouldn't include water carbon dioxide. Right? Don't look at water carbon dioxide. Carbon dioxide is a vapor. And then there are some ternary systems. Right? We're not going to look at those ternary systems either. Okay, so I want binary systems. So water plus a second component in this case, and try and choose a variety of second components. Okay, and if you need help identifying systems, let me know. I'd be more than happy to help you. Okay, but I do want to give you some freedom. I don't want you to have to look at everything, but try and choose a couple. Okay. All right.
So one of the systems I'm going to look at is water acetone. So if I click at water acetone, okay, it brings me to the data page. Okay, so it has molar masses and casses up here. We won't need those. Okay, what you will need to note though is when I clicked on water acetone, let me click back. Right, even though water is my component, right, I'm assigned water. I click on water acetone. Right here, right, this is indicating that they're actually calling acetone component 1 and water component 2. All right, so it's important to keep track of those as we enter in our properties. Okay, tells us there's no miscibility gap. That's good. That means we have a single liquid phase. Okay, and then you'll notice for this case, I'm going to have multiple sets of data. So what's given here is at 293.15 Kelvin. Here's my excess enthalpy or delta H of mixing data. Okay. You'll see there's also a set of data available at 308.15, 323.15, right, and then they have a little sketch at the bottom. Okay. So if I have a binary system like this, for which there's data available at multiple temperatures, only look at one. Right? We will only look at one. All right, maybe choose the one with the most data. So say 308.15 here. Okay, but only look at one. You don't need to look at all of them. Okay, cool. All right, so now how I'm going to make predictions with this is, one other point. So we said we're going to look at pressure dependence. You'll notice in all of these, so essentially for all the systems that you should look at, they're only going to report temperature up here. So if I think to a single phase binary mixture, in addition to composition, right, I need temperature and pressure to characterize the phase. Okay, but we're only given temperature. So you can assume that all of these systems are at 1 bar. Okay, so you can assume that all the systems are at 1 bar or atmospheric pressure. Okay, the assumption is here when I'm modeling these condensed phase properties that they're essentially independent of pressure, and so pressure is not even reported. Okay, but we'll look at that a little more. Okay, all right. So now if I go back to my project 2 folder, okay, you're going to notice 2 other directories in there. Okay, one is M-Files. Okay. What M-Files are going to correspond to are the function files that are going to be needed in order to perform the calculations. Okay. And then similar to before, you'll see an example directory. Okay, and so we'll look at this example directory, but this is essentially what you can just download, and then you can update for your systems of interest. Okay, you can even leave the systems that I did in there, and we'll walk through a couple of examples. Okay, so if I go back to project 2, all right, so you're going to want to download example. So it'll download as a zip, unzip it, and put it somewhere on your computer so that you can perform some MATLAB calculations with it. Okay, so I'm going to pretend I downloaded it. So I just opened it up. And I'm going to go to MATLAB, okay, and I have my example directory here, right, and I have it open, here. Okay. The files that you saw in the M-Files directory, so there are these 4 right here. You shouldn't have to touch those at all, and I would encourage you not to touch them, so you can just leave it as is. But in the example directory, what you'll see is I have an acetone benzene at 318 Kelvin and an acetone water 308 Kelvin M-file set up for those 2 systems, and those will be the 2 systems we'll look at here. Okay, to see. So when you run a new system, that's what you have to create, right? So let me walk you through these 2 examples, and then we'll set up a brand new one. Okay, but if I open up acetone water, okay, so in the top I'm going to have input to modify, and then below this double line you shouldn't have to touch anything. Okay, so only look at lines 1 through 37. Well, lines 1 through 37 because I have data typed in here, but up to this double commented line, below that you don't have to do anything. Okay, so I'm going to go back to acetone water. Okay, where are you? You're right here. Okay, all right, so what do I need to do? Okay, well, so acetone water, okay, I'm going to look at binary system of acetone water. So component 1's acetone, component 2's water. Okay, so here's my temperature, 308.15 Kelvin,
And again, I said unless it gives you a value, you can assume that all of the data is at 1 bar. Okay, so I have my temperature in Kelvin, pressure in bars that I can update. Then the next thing to update is I need to know my critical temperature, pressure, and eccentric factor for each component in my binary mixture. Okay, so in our mixture of acetone water, acetone's component 1. Okay, so what I have listed here is critical temperature of acetone, critical pressure of acetone, and the eccentric factor of acetone. And then for component 2, I have critical temperature of water, critical pressure of water, and eccentric factor of water. So I found these from the appendix in the back of the text. You could also get these from NIST webbook. Right? So NIST webbook, you type in a component and you'll be able to find the critical properties. Okay. If you have issues finding critical properties for your component, send me an email and I'd be more than happy to help you. Okay, so these I need to update for my system. All right, then next comes I need my reference data. Right, I'm going to put reference data in there to compare to. Okay, so what I have here is I'll just outright delete this so you can see it in action. Okay, so what I've done is I've copied the URL up top to kind of serve as a diary entry. Okay, that way if there's any questions, I could just go right back to that URL and get the exact same data. And then I have this set up so that I can just copy and paste the data from online. Okay, so I'm literally just going to copy and paste. Okay, so remember MATLAB, I can use spaces or commas to separate my data. And when I enter a matrix in this way, return is interpreted as a new row. Okay, and so I'm not going to be super worried about making them look nice and pretty, but close enough, right? They're separated by tabs. That's good. Okay, and then the last two things to update is this variable fig name. So when we create figures, they'll begin with acetone water. Okay, this way for this project you can do all of your calculations in the same directory. So put a unique name on there so you're not overwriting other calculations or mixing things up. And then in the next line is when we create our figures, this is the title that we're going to put at the top of our graph. Okay, so make these look good for the system. Okay, fig name, I would just list the binary system because we'll use this to name some files and such later on. Don't use any spaces. For fig title, you can put spaces in and make it nice and descriptive and make it look pretty. Okay, so once I have that updated for my system, okay, I'm going to just click save. You could just press run, or you could type in the command window. But if I press run, okay, I'm going to get two figures first. Okay, so this is acetone water. Okay, and so what I have in figure 1 is this is delta H of mixing in joules per mole, the same units as NIST uses, versus liquid phase mole fraction. Okay, and then the circles are going to correspond to my reference data. Okay, and so acetone and water is unique in, remember component 1's acetone. At low water compositions, I actually get a negative delta H of mixing. Okay, so my system is exothermic, heat is liberated upon mixing. Okay, so mixing is favorable. Okay, so remember this is pure water, so this is me adding a little acetone to essentially my water-rich phase. Okay, so it's negative, but then it crosses 0 and becomes positive. Okay, so this is the limit in which I have pure acetone. So if I have pure acetone and I begin to add a little water, mixing is actually endothermic. Right, heat is actually consumed, right, in order to maintaining constant temperature. Right, and so the idea is when I have pure acetone, add a little water to it, water's not too happy or comfy. Right. So this is a pretty unique system in which I have a negative and positive region of my delta H of mixing curve. Okay. And then these lines, okay, these are going to correspond to our predictions. So solid lines are going to correspond to predictions with my SRK equation of state. Dashed lines are Peng-Robinson. So what I have in my solid or dashed red lines is the predictions with SRK and Peng-Robinson, assuming Kij is equal to 0. Right, so assuming a van der Waals mixing rule, Kij is equal to 0, so geometric average of those cross interactions. And what we find is that with Kij of 0, our predictions are, well, way off. Right? Predictions are way off from our reference data. And then what's shown in black here, all right, so now my dashed line and solid line are on top of each other. This is the predictions with the cubic equation of state with an optimal value of Kij. And so Kij is found by minimizing the squared difference between my predictions, which is the line, and my circles, my reference data. Okay, so that's me, or us, after fitting Kij. Okay, so that's cool. And then what's shown in figure 2 is I take the Peng-Robinson cubic equation of state, so results with Peng-Robinson and SRK with the optimal Kij, right, are going to be virtually indistinguishable from each other. So in figure 2, what I've done is using the optimal Kij for Peng-Robinson, I'm again predicting delta H of mixing versus x1, but what I'm doing is I'm changing the pressure from 1 bar all the way up to 100. Okay. So in this system of acetone and water, so this blue line is 1 bar, so going from 1 bar to 10 bar, it looks like there's essentially no difference in delta H of mixing, right? It's minimal at best. But then, there are some larger deviations as my pressure increases, right? So, 100 bars, we're predicting the same sort of functional form, but numerically, here there's a difference of about, say, 50 joules per mole. Okay. So I'm going to close this out, okay? And when I run, okay, acetone water, you're going to see 2 .dat files, 2 text files are created. Okay, the first one, okay, so if you want to open it in a notepad, one thing I can do is if I right click, I can say open outside of MATLAB. Okay, so they're going to be comma separated vectors, something I could readily copy and paste in Excel. Okay, here's the optimal Kij value using SRK and Peng-Robinson, right? So about negative 0.4. So negative being that we need to strengthen our cross interactions relative to that of geometric average, right? And so Kij is negative, and it should make sense. So if I run it again, right? So these are rather quick. Geometric mixing predicts as a large positive delta H of mixing, where with my optimal Kij, I predict a negative value, right? And so this is underestimating the cross interaction between those two compounds. So negative Kij will strengthen those cross interactions. Okay. So, like I said, this is set up to be a CSV. Okay, so what that means is if I copy this, okay, and I were to go back up to our drive, okay, an example, if I was to create a new sheet, okay, I could call this first sheet acetone water. And so then if I paste here, remember this was the annoying data split text to columns, right? This is Kij opt SRK, Kij opt Peng-Robinson. All right, so I've got them in there. Okay, cool. The other text file you'll see created, besides this acetone water Kij SRK Peng-Robinson, okay, so no. Right, fig name acetone water Kij SRK Peng-Robinson. Right, so I add this as an extension. The second one, ref SRK Peng-Robinson, is a CSV as well that'll contain all of my predictions. Okay, so if I paste this here, split text to columns. Okay, so this is x1. Those are the same x1 values from the reference data. Here's our reference data. Here's SRK using the optimal Kij. Here's SRK using Kij of 0. Here's Peng-Robinson using optimal Kij. Here's Peng-Robinson using Kij of 0, right? And so you can readily put all the numerical values in Google Sheets if you like. Okay. So let me close that. So I have all those there. They're nicely named. I also created a figure. All right, so acetone water PNG. If I were to open that up outside of MATLAB, it's just a copy of my plot. And actually, notice a typo here. right? I'll re-upload this to MATLAB. So if I rerun it, I accidentally named them the same thing. So now I'll have acetone water PNG, which is my first plot. And then acetone water, where are you? Pressure, Peng-Robinson pressure PNG, second plot. Sorry, I just noticed that I forgot to update the name of the second figure, but it's fixed now. Okay, so I'll re-upload that latest code. Okay, cool. Okay, so that's acetone water. The other example I have is for acetone benzene. Okay, so if I go back here, okay, I click back. Okay, let me go to acetone. Right, so you'd be looking under the same category for both. Acetone benzene at 318.150. Okay, so again, component 1 is acetone, component 2 is benzene. Okay, I'll copy these just for demonstration purposes. Okay, but if I were to look at acetone benzene at 318, right, I need the temperature, 318, the pressure, 1 bar, unless you're told otherwise. Then here's the critical temperature, pressure, and eccentric factor for acetone. Temperature in Kelvin, pressure in bar, and eccentric factor. Component 2 is benzene, so here's the critical temperature, pressure, and eccentric factor for benzene, right? And Kelvin, bars, and omega is dimensionless. Okay, so if I imagine copying and pasting this, bam, copy and paste in my reference data. Okay, and then let me copy and paste in the URL just for completeness. If I take this to be my diary, bam. Okay, I'm gonna save it, and then you just need to upload, update your titles. Cool. So fig name acetone benzene, then my fig table or figure title, and so just like that, then I can run it. Oh, forgot before. I need to update this example. This is bam. Okay, don't worry, you'll get the latest code. You won't have to do anything like that. Just remember, only read down to these double commented lines. Okay, so I run it. So figure 1. All right. So here's delta H of mixing versus x1. So here, this circles again are corresponding to my reference data. So here, over the entire range, enthalpy of mixing is positive. Mixing is endothermic. Okay. Unfavorable interactions. Okay, so circles are my reference in this data, or DDBST data. Solid black line corresponds to my SRK equation of state with the optimal, hold on, my colors. What am I doing here with my colors? I think my colors are off, and oh, no, I'm sorry. Sorry, I had a moment there. Apologize. So SRK, the black solid line, is my SRK equation state with my optimal Kij. Solid red line is SRK using a Kij of 0, right? Standard van der Waals mixing rules. So here's a case where with Kij of 0, we predict that delta H of mixing is 0 or less than 0. We predict, exothermic mixing, favorable cross interactions. And so then I would bet that our Kij is going to be greater than 0, because what we need to do is scale down those cross interactions. Okay, dash line corresponds to Peng-Robinson, and those results are virtually the same, which is why you can't see them. Okay. This is, and actually let me bring up Kij while we try and talk about it qualitatively. So acetone benzene, okay, I've got Kij, all right, so here's a case where Kij is 0.01. Right, in both cases, my Kij is 0.01. Okay, so actually let me, we'll just go to our Excel sheet and we'll copy it. Okay, so this is acetone benzene. Okay, I'll do data, split text to columns. Actually, all right, so this is Kij opt SRK.
opt Peng-Robinson. Okay, so Kij is just 0.01. Right, and this is pretty fascinating. If I look back at my plots, right, Kij of just 0.01. Right, so we said we expect it to be positive as it scales down the interactions, but just the value of 0.01. Right, come on, that seems so tiny. Is all that it takes to go from here to here. Right, and so hopefully this emphasizes the sensitivity of your equation of state on, or the sensitivity of your predicted properties on Kij. All right, and delta H of mixing, you have to imagine it's very sensitive, because much like Kij being used to estimate your interaction term for your mixture, delta H of mixing is related to our interactions in our system. Okay, cool. All right, now if I look at pressure dependence, right, and now in this case for acetone benzene and going from 1 bar to 100, delta H of mixing essentially doesn't change. All right, so delta H of mixing here is essentially insensitive to pressure. Here we went up to 100 bars, so all the way up to 100 bars. Okay, and in terms of tabulated data, all right, so here would be acetone benzene ref SRK Peng-Robinson. If I open outside of MATLAB and copy that, okay, I can paste it. Data, split columns. So this is X1. Here is SRK with our optimal Kij. This is X. Boy, all these tongue twisters. Let's. Alright, bring it back up, right? SRK with my optimal, right, it's pretty close to my reference data. SRK with the Kij of 0, right, is that guy. Okay. So this should be SRK. I apologize again, I am having a moment. This should be SRK with Kij equal to 0. Oh, boy. Again, I apologize. This is reference. This is SRK opt. This is SRK with the Kij equal to 0. This is Peng-Robinson opt. Peng-Robinson the Kij equal to 0. Alright, when Kij is equal to 0, when I get these negative values, my optimal values, they'll predict a positive delta H, just like we should. Okay? Yeah, see, I got it right there. But then you could add the temperature, you could add your system name, and everything else to this sheet, and you could readily, try and quantify your deviations between your predicted values and your reference values over here. All right. And so just for illustration, okay, those are two examples. Let's try and look at a different system. Okay. All right. So if I were to go to DDBST, okay, maybe let's just stay in this acetone category. So we just looked at acetone benzene. We've also looked at acetone water. Let's say I want to look at acetone chloroform. I say, hey, that was the cool system we talked about for maximum boiling azeotropes. So I click on acetone and chloroform, and I get this. Okay, so let's try and perform calculations for acetone chloroform at 298 Kelvin, 298.15 Kelvin. So I'm come over here. Here's acetone benzene, and I'm going to save as. I'm going to save a copy as acetone. Acetone chloroform, and it was at 298. Okay, so we're at 298 Kelvin. Okay, I'll save it. Okay, so then what needs to get updated? My temperature's 298. Okay, unless we're given another value, we'll take our pressure to be 1 bar. Now, critical properties. Okay, so I'm going to go to the back of our textbook. So remember, there's a scanned copy of our appendix available on Canvas. Alright, so I am in Appendix A. So acetone, I already have in there. I don't need to update acetone at all. Okay, let's see. But am I lucky enough to have chloroform here? Probably should have worked all these things out before the screencast. Yes, chloroform is here. Okay, and so for chloroform, okay, I have 536.5 Kelvin. Critical pressure is 55 bars. And omega, well, an omega is not provided in the table, which suggests an omega of 0. Okay, so I'm going to save this. Okay, also I'm going to update the name. So here I have a comment that this is acetone. This is chloroform. Okay, now we just need the reference data. So I'm going to copy my URL so I can add it to my little diary. Okay, I'm going to delete this delta H of mixing data. I'm going to copy this like you have in the table. And you already noticed that these are big negative delta H's of mixing. All right, remember we have favorable cross interactions between acetone and chloroform. I'm going to tab that in so it looks somewhat pretty. Okay, I'm going to update my name. This is acetone. Chloroform. This will be acetone. Chloroform at 298.15 Kelvin. Okay, so I'm going to save it. And then I'm going to run it. Okay, and just like that, I made my predictions. Okay, so if you want to get this legend out of the way, I can just click on and drag it. Okay, all right, so what do we have here? So solid black line is SRK with my optimal Kij. Solid red line is SRK with a Kij of 0. Okay, so if I were to use standard van der Waals mixing rules, Kij of 0, I would predict this. It looks like I predict delta H of mixing to be slightly positive. So I'm predicting slightly unfavorable interactions between the two components. Okay, but with Kij, and when I fit Kij, SRK and Peng-Robinson both can do a very good job correlating or predicting our binary data. Okay, and we predict that delta H of mixing is negative. Okay, negative favorable cross interactions. And so what that would suggest then is we have a Kij that's going to be less than 0, right, in order to get those favorable cross interactions. Okay, and before we bring those up, if I look at this term or this plot, so remember here we're just taking delta H of mixing predicted with Peng-Robinson and varying the pressure. And so again, from a pressure from 1 to 100 bars, delta H of mixing essentially is insensitive to pressure. Okay, so this is interesting because these results for acetone chloroform in terms of pressure dependence are just like acetone benzene, where the results don't really change with pressure. But if you remember for acetone water, yeah, the changes were still pretty small, essentially negligible still from going from 1 to 10 bar, but beyond that they became significant. Okay, so if let me just, come on, here we go. Let's just try and minimize this animal so that I can bring lots of different things up at one time. Okay, bam. So let's keep these up so we can keep looking at them. Bam. Okay, if I were to look at my text files, so this is acetone chloroform. Okay, so in terms of my Kijs, okay, here's my Kijs. We get negative Kijs. Okay, in terms of magnitude, Kijs, negative 0.1. Right, so it's in the 10th. So it's much larger than acetone benzene. We were looking at positive 0.01. Okay, so these values seem to be changing a lot, all right, or vary a lot from system to system, both in terms of being positive or negative, and then their actual numerical value. All right, but just look at acetone benzene for 0.01. It makes all the difference in the world in terms of making quantitative predictions. So I'll go back to my spreadsheet. I'm going to create a acetone chloroform tab. Okay, I'm going to paste this in. Okay, so this is SRK and Peng-Robinson Kij opt. Okay, both are negative. Negative Kij, meaning we're strengthening those cross interactions relative to what van der Waals would predict. Okay. So if I go back down here, close this. If I want all of the raw reference data, well, here it is. Split the columns. X1, ref. This is SRK opt Kij, SRK Kij of 0, right? So we predict values that are slightly positive. Peng-Robinson opt and Peng-Robinson with a Kij equal to 0, right? If we were just to use Kij of 0, right, we're not even going to capture the correct physics. All right, with a Kij of 0, we predict delta H's of mixing which are positive, unfavorable cross interactions, where in reality they should be negative. We have favorable cross interactions, association between those two components. Okay, and I could update this. So say all the systems I were looking at were acetone. All right, I could call this sheet acetone. Right, and cool. All right, and now you don't need to worry about making your figures. Right, they're all here in PNGs. And so just like before, once you've looked at your 10 systems, right, so you could just save a copy of this for your new system, update it and run it. Once you're done, you could just take that entire directory you just created, and wham bam, you could upload it here to project 2, right? So if your system were acetone, you could upload an acetone folder here, so that your pictures and all your results are readily available to everyone else. Okay, and so with that, I will stop recording. If you need any help, let me know. If you want me to make another screencast to give you some more information or insight or more instructions, please do not hesitate to ask.